over the same region that we integrated over which we integrated originally. So that region we should be familiar with goes from 0 to 1 with respect to x, from 0 to the square root of 1 minus x squared with respect to y, and from 1 minus the square root of 1 minus x squared minus y squared to 1 plus the square root of 1 minus x squared minus y squared. In this case, our delta is 1 plus y. So we can write out the integral and then that's going to be y times 1 plus y dz dy dx. And I think I wrote this dz up here. That should be a dx. I'm going to stop and repair that. It should be clear that if gravity was acting in the x direction, then this object would tend to rotate about the z-axis, and that everything, because of the symmetry of the figure, would be identical. In other words, the distance of every slice from the z-axis is the same as the distance of that slice from the x-axis. So we call this the moment about the xy, or the xz plane. So that's mxz. The moment that results from a changing y is relative to the plane perpendicular to the y-axis. So that's the moment xz. We could similarly find the moment about the y-axis, so that if the x-axis in this picture, let's rotate the x and y axes so that we go this way. No. Excuse me, I was debating how to picture this, and I think I'm just going to do it this way. Here's our picture again. Kind of a badly drawn circle in the y direction. If I'm slicing this relative to the x-axis, then the slices are going to look something like this. And we can imagine, if the x-axis goes this way, that we have some variation in the amount of mass slice by slice. Now the density gets bigger as we move this way, so that the bigger slices are going to both have a bigger average density and a bigger volume, which means that the slice closest to the y-axis is going to be both the thickest and the one that comes all the way out to density 2, although a lot of that slice is in here near the z-axis where the density is 1, and that these densities and volumes combine to give us some curve. It's actually going to be kind of a curve that's concave upward as we move in this direction. And those masses are going to create a rotation about this fulcrum. Any small volume increment is going to have a moment that's going to equal, again, its mass, which is 1 plus yj star multiplied by the volume increment. But now the fulcrum is here, and the distance from the fulcrum changes with x, so that our moment is going to be a xi star times the mass. So this is called the mass, and this is what we call the moment arm. The distance of the mass from the axis or the fulcrum, the axis of rotation or the fulcrum. And the total moment with respect to this rotation about this direction is going to be the moment perpendicular to the yz plane, and that's going to be the integral of x times 1 plus y dz dy dx, with, I'm just going to put etc. for the lower and upper integrals, lower and upper limits on the integrals, same limits that we had previously. Similarly, we'll have a moment about the xy plane, and that would be the tendency of this solid to rotate due to some force in the z direction, rotating this way. And that moment would be, again, the triple integral of, in this case now, z times 1 plus y dz dy dx. Now the 1 plus y dz dy dx is the same for all three moments, because that corresponds to what? That corresponds to the mass within our typical volume increment. So that this part here is the mass, this part, and this part represents the mass of a typical volume increment, whereas the y, the x, or the z represent moment arms. And I won't label it here, there's no way to get an arrow in there, but we understand that we have moment arm perpendicular to the xz plane, that would be y. Moment arm perpendicular to the yz plane would be x. Moment arm perpendicular to the xy plane would be z. From what you've seen about these integrals, it should be clear that when we integrate with respect to z, in this case or this case, this product, the y times 1 plus y or the x times 1 plus y, can be factored out of that first integral. That's not the case if we have this function. We have to integrate z with respect to z. And as it turns out, we have integrals that follow different patterns as we work from inside to out. So let's contrast those.